Hello, ladies and gentlemen. This is Mr. Jones talking to you. Just want to let you know that I am always there with you. Maybe not in body, but in spirit at least. But enough of that touchy-feely, feel-good stuff. Today, we're going to talk about elastic potential energy. We took a look at this a little bit first semester when we did the thing with the carts and the springs. So you guys should be familiar with potential energy, elastic potential energy, spring constants. We're going to kind of go in depth on those, hopefully answer a couple of the questions you might still have. Now I know what you're thinking. Mr. Jones, those are pictures of springs, and you would be absolutely correct. This top spring up here, in fact, is an uncompressed spring, so this would be like your cart when that little plunger is sitting pushed out, or sitting all the way out. This right here is a compressed spring, so one that's been pushed all the way in. When we push a spring like this in, we would say that it has elastic potential energy because in order to compress it, we had to put a force on it. That force moved it a distance, which means we did work. If we do work, we are transferring energy from one system to another. So your body did work on the spring, and then that energy that you put in is then stored inside of that spring so that when it is released, it pops back out to the original length, releasing that energy in the form of kinetic energy. And as with all forms of energy, energy has to come from somewhere. So the work that you do to go from this point to this point right here is equal to the energy that is then released when the spring goes out. So if it takes 1 joule of energy to compress the spring, when you let it go, it's going to push out with 1 joule of kinetic energy. Nothing too earth-shattering there. But if you think about springs, there's different types of springs. Some of them are really hard to push in. Some of them are really easy to push in. So there's different types of springs. They're all going to release elastic potential energy. But depending upon the stiffness of them, the size of them, the thickness, there's going to require different amounts of force in order to compress them. And if it takes more force to compress them, that means they're going to release more energy when they're uncompressed. And we keep track of that like force requirement or thickness or strength of a spring with a constant that is a lowercase k, and that is called the spring constant. So I gave you some practice problems last semester. One of them asked you about the spring constant. Some of you guys didn't know where it was. This little sheet right here, you should have a copy of this. If you don't, you can type it into Google and get a new copy, or you can grab one from the front of the classroom. This is where you should go anytime you have a question about something, because this is literally all the answers to all of the mathematical questions in this course listed on this sheet. So anytime you're asked about something, this is also a good strategy you have for the test. If you have no idea how to do something, come to the sheet and just read through it, and you could probably find most quantitative things that you need to on this sheet. So for example, if we come down on this side, oh, hey, what's this? Spring constant is a lowercase k. And so then we can look through this, and we can find all of the areas that have that k, and then what would be useful for us in order to solve a particular question. So I see that lowercase k a couple places. I see it right here where it says that force is equal to k times x. I see it right here. We can see the potential energy of a spring is 1/2 k times x squared. That one right there, this is the one that we did in the lab on before break. So it shows us that the potential energy of a spring is equal to 1/2 the k x squared. So what you guys found in that lab is that the spring was equal to some constant times the distance it was compressed squared. In this case, that number that you found, the slope of your linear graph, would have been 1/2 the k of the spring for those guys right there. So I think a lot of them were like 0.2. That means the actual spring constant for those would be 0.4. And then finally, the k shows up right here. And so this one right here isn't going to make much sense to us yet, but we're actually going to use it in a lab today. So there's a couple ways that we can find the spring constant. We'll go through them. This first one right here, the first equation on that sheet says that the force is equal to the spring constant times the distance that the spring is compressed. So let's say, for example, that we have a spring, here it is uncompressed, and we put a 1 Newton mass on it. When we put that 1 Newton mass on it, it causes the spring to compress 1 meter. So then to find the spring constant for this particular spring, k is going to be equal to the force divided by the displacement. And so in this case, it's a 1 Newton force, and it compressed 1 meter. Therefore, the spring constant for this guy is 1 Newton per meter. And so then that constant stays with that spring. It means that particular spring requires 1 Newton of force for every meter that it moves. We can then use that k in any different equation or different areas that we need to. So for example, if we wanted to find the potential energy that is now in this spring, that is stored up in the spring that was put in by that 1 Newton mass, we could plug it into the U of S equation. So U of S equals 1/2 kx squared. So the potential energy of this spring would be 1/2 times 1 times 1 squared. And so essentially a half. So that means that this spring now has a 1/2 joule of energy stored up inside of it. When that weight is removed and it can decompress, it will release 1/2 joule of kinetic energy. So this method right here of hanging or setting a mass on a spring in order to find out what its spring constant is known as the static method. It's the static method because the spring itself is not bouncing, it's not moving, you're just letting it hang with a weight, or be compressed with a weight, letting it sit there in static motion, and using that to find the K. So with the static method, the spring is sitting still, but we can also use what's called the dynamic method. With the dynamic method, the spring is actually moving. And for the dynamic method, we have to use a different equation, and that one is going to be this guy. So what this says is that the period is equal to 2 times pi multiplied by the square root of the mass that is hanging from the spring divided by the spring constant. So instead of a spring with a mass sitting on top, let's imagine a spring with a mass hanging from it. If this were the case, you could probably picture this. So imagine this up here is secure. Draw a little line to mean that it's attached to a ceiling or to it. And then imagine that you grab this mass right here and you pull it down and then you let it go. What's that spring going to do? Well, it's going to bounce it back up, and then it's going to go up, and then it's going to come back down. And what you're going to get is an oscillation of motion. And so think of a spring or like a bungee cord or something. When it falls down, it stretches it, comes back up, and it will oscillate back and forth. Those oscillations have what's called a period, which we symbolize with a capital T. We're going to have an entire unit on oscillation and oscillatory motion. I don't know if that's a real word. But what a period is how long it takes, how many seconds it takes for an object to make one complete oscillation. So in other words, if we were to pull this down and then let it go, how many seconds would it take it to go up and then come back down to the position where it was released? So if we pull it down, it goes up, comes back down, and that takes 1 second, then the period would be 1 second. If it takes 3 seconds to go up and then come back down, then the period would be 3 seconds. So the dynamic method of finding the spring constant of a spring is using the period. What you do is you hang a mass from it, you know the weight of the mass, and that would be what you put in for m, except it shouldn't be newtons, it should be kilograms since it's mass, not force. You pull it down, and then you let it go up and then come back down. You time how long it takes it to go up and come back down. However many seconds it takes would be your period, and that's the number you plug in there. And then you can rearrange this equation in order to solve for your spring constant. Oh, and hey, that's what you're going to do in today's lab. You're going to determine the effective spring constant. We'll talk on what effective means, but first off, you're just going to find the spring constant for a spring using two methods. You're going to do it once with the static method and once with the dynamic method. Then what you're going to do is you're going to figure out what happens to the spring constant when you line up two identical springs in different ways. So, for example, we've got this spring right here, and all of these springs are identical. So this one right here is the same as that one, that one, that one, and that one. So as individuals, they all have identical K's, spring constants. But let's say that this one right here has a spring constant of 3 newtons per meter. What is going to happen when you take two of those springs and line them up like this? Will this constant now be 6? Will it be 1.5? Will it be some outrageous number? Will it be 3 squared, 2 cubed? And then what if we put them in parallel like this, so next to each other? What's going to happen to the spring constant there? So your goal for today's lab is to find the spring constant of a single spring and then take two identical springs, so find this one a match, one that's identical to it, line them up in series like this, line them up in parallel like this, and figure out an equation to find out what the spring constant would be for each of those. The goal for that then is, what if we had 3 identical springs? What would the spring constant be? What if we had 1,000 identical springs? Then what would the spring constant be? You should be able to derive a mathematical formula for figuring out what the K is for springs in series based upon the number of springs or in parallel based upon the number of springs. This is exciting, and I know you're ready to go, but hang on. Down at the bottom of this, it says something about a poster. Don't worry about the poster. Instead, on Google Classroom, you're going to be doing one of those explanations like what we did last time with the Conservation of Energy Lab. So in this case, you're going to be talking quantitative and qualitative with these spring constants. On Google Classroom, make sure you look at the example of a good quantitative and qualitative explanation I gave you. Your qualitative explanation should be describing the situation, so what happens. With the last one, the Conservation of Energy Lab, you should have talked about how the relationship is exponential. So when you push it back, it makes an exponential, releases an exponential amount of energy based upon the compression. That's what gave us the x squared. Quantitative then has an equation, and that equation is usually backed up by data and a graph. Graphs are a great way to do it. Make sure they're linearized, and then you use the y equals mx plus b in order to get that equation. Make sure your equation doesn't say y, mx, and or b. It should have the variables plugged in there. Your slopes, if you have one, should have units on them as well. If you go back and you look at your last lab, I put comments on there what kind of things I dinged you for. So make sure you go and look at those and that you try and fix it for this next one. As I say on the classroom post, it's super important that you're able to come up with these quantitative and qualitative explanations. They're going to come up on the test. There's an entire free response question that's literally called the quantitative qualitative question, where you have to be able to do this. So we'll be using springs and the hooked masses for today's lab. So the springs are in little white cardboard boxes that you'll see, and each one of those boxes is a set of 5 different springs. And so you're going to want to find 2 springs that have the same constants, and you'll be able to look at them and tell which springs are identical. So make sure you grab 2 identical springs. They won't be in the same box together. You'll have to grab one from one box, one from another. The only materials you should need for this lab are going to be the springs, the hooked masses, a meter stick, and a stopwatch. Make sure that you collect very, very careful data, because you want your numbers to give you good answers so that you wind up with a good quantitative and qualitative response. So when you collect numbers, make sure that you get at least 7 different variables. Make sure you're doing at least 5 consistent trials of each, and that you average those in order to get your numbers. Don't just bust through this once, because you're not going to get results that you like. You're not going to get results that I like. Remember, I am not in class right now to watch you doing this, and so I can't just say, they had a nice pair of shoes on that day, I'll go ahead and give them credit for it. All of my understanding of how you did on this lab is going to come from what I see on Google Classroom. So you want to make sure that you collect very good data, compile it well, and that you submit it to me so that when I'm sitting at home, I'll be able to grade it with my cup of coffee. And kids screaming in the background. Well, good luck. That's your mission for today.